apart from this 2 pi factor. You can get rid of that 2 pi by defining 2 pi to the minus half times f as the Fourier transform operator, and then of course its fourth power is the identity operator. Now these factors are used in Fourier optics very often. It is very common to use these because, as you know, a thin lens essentially acts as a Fourier transform device. So they have immediate application, but they follow from this simple mathematical property here. We have also been talking about the fact that momentum space wave functions are Fourier transforms of position space wave functions. If one is an L2, the other is also an L2, square integrable. So in some sense we would like to be able to be assured that one of them, the two descriptions either in position space or momentum space are unitarily equivalent. We would like to be assured of this, which means we need to show that we already know this from Parseval's formula, but we need to show explicitly that the Fourier transform operator is a unitary operator, preserves probability, etc. So let us see what happens. We can directly establish this or not. Yeah.
Is this the only transform whose square will be the parity
No,
operator?
of course, no, that is not true. Yeah, I mean you can't, it is like asking what is the square root of the identity matrix? 2 by 2 matrix, let us take 2 by 2 matrices. What is the square root? Give me a matrix whose square is the identity matrix. Of course you would give me the identity matrix itself, you would give me -1 on the diagonals, that too is true. But the fact is that if you give me any matrix of the form A dot sigma, make this a unit vector dot sigma, n1, n2, n3 such that n1 squared plus n2 squared plus n3 squared is 1, and I square this guy, I am going to get the identity matrix, right. So you really have a continuous infinity of such square roots, if you like. So the question of when you have a unique square root for an operator is an interesting question. Well, if the operator should turn out to be what is called a positive definite operator, then there exists a unique positive definite square root for this operator, and that is useful in many contexts. But no, not the Fourier transform is not that sort of operator at all. You know, this business of taking square roots is very interesting because square roots of operators are really profound, very many profound things follow from this. If you took the Klein-Gordon operator, the box plus m squared operator, and took its square root, you get the Dirac operator. That is what happened when Dirac linearized this box plus m squared and so on, you got the Dirac. You could also ask what about other operators like translation operator, what is its square root, and then you end up in quantum field theory with what are called supersymmetric operators. So supersymmetry follows the operator, something which is like effectively the square root of a translation operator. We will talk a little bit about this when we do the Klein-Gordon, and talk about the Klein-Gordon equation. So let us establish the unitarity of this operator, this Fourier transform operator. I recall to you that if you have an operator k, then by unitary I mean k dagger should be equal to k inverse. That is what I mean by unitary. So I need a unique inverse. I need k dagger equal to k dagger k equal to the identity. If you have finite matrices, then there is no problem, because finite dimensional matrices, if you have u dagger equal to I, this will imply that u dagger u is also equal to I, because then the right and left inverses are the same. But in an infinite dimensional space, this is not guaranteed. Unitarity requires both these. You need both these conditions, they are different conditions. The right inverse and the left inverse must exist and be the same thing, be equal to u dagger, the adjoint of the operator u. So we need to establish this, but this is an integral operator. First we need to know what is meant by the adjoint of this integral operator. Well, if it is a matrix, then I know what is meant by the adjoint. It says take complex conjugate transpose, that is the adjoint. On the other hand, what is it for an integral operator? Let us start again, and how do you find the adjoint? Well, you take this k, act on any vector in the function space, take the scalar product with some other vector in the function space. So after you act on this, you identify k dagger by saying, is there an operator k dagger such that this is equal to that? for all pairs f and g in this space. If there is, then this k dagger is identified as the adjoint of my operator k. So let us see what it does for integral operators. The translation of this says take integral k of x comma y, f of y, you integrate over whatever the range is, that is this vector, and now take its scalar product with this function, which means you have g star of x integral dy, oh sorry dx. That is what the left hand side is. Okay. Is this clear? So it says f is represented by f of y in that function space, this is represented by the kernel k of x comma y, and I integrate over y, I get another element of the function space as a function of x. Now I take g star of x, that is this guy here because it is a bra vector here, integrate over x, and that is my scalar product. I need to be able to write it in this form. So what do? The first thing I do is to interchange order of integration. So I get dy integral dx g star of x k of x comma y f of y. That is the first step. Next let us exchange the labels x and y. So this becomes equal to integral dx integral dy g star of y k of y comma x f of x. Which I can write as equal to integral dx integral dy, and then let us call this k star of y x g of y star f of x. Okay, where this is the complex conjugate integrated over dx and dy. Okay. But this guy here is precisely this, and when it is multiplied by f of x integrated over x, I get this thing here. So what does this mean? It means that if this is represented by a kernel k of x y, this operator is represented by the kernel k star of y x. But that is exactly what happens in the case of matrices. After all, what is a function space? It is just a continuous analog of matrices in which the rows and columns, essentially the labels, the row and column labels, these indices become continuous. So if I say aij star or a in the complex the ijth element of the adjoint of a matrix A is aij star equal to aj I whatever. But that is exactly what I am saying here. I interchange these x and y, and then I take a complex conjugate, which is what you would expect, except that we have painfully gone through it in this fashion. Now what about the case of Fourier transforms? Well, the kernel in that case, remember I had f tilde of k equal to dx e to the power minus ikx f of x. So the kernel in that case was this guy. And what about the inverse transform? It was e to the plus ixk. So the other kernel was, apart from this 2 pi factor, you had, in the other case you had dk e to the ikx, or let us write it ixk f tilde of k. That is what has happened here. So I took this kernel and I inverted it, I flipped x and k, that does not do anything, and then it is e to the I x k, complex conjugate transpose. But that is what has turned out to be the adjoint. So this is immediately a proof that the Fourier transform operation is in fact unitary. You want to make sure there is an I, a unit operator that appears, then define, instead of what we have here, call it 2 pi to the minus half times this Fourier transform operator. So unitary operator. Perhaps we should. Okay, so now let us take a look. Now that we have seen that the Fourier transform operator is unitary, let us ask what about the eigenvalues and eigenfunctions of this operator, if any. Okay. Now as you know, when you have an operator and you would like to define its spectrum, eigenvalue spectrum and corresponding eigenfunctions, you need to specify the function space first or whatever space you are on for the operator. You need to specify the vector space, the linear vector space, and let us take again, since that is the most common case, L2, the L2 space. So the specific question we are asking is, what are the eigenvalues and eigenfunctions, if any, of the Fourier transform operator in L2 space? Well, we can prove this rigorously, but I am going to do this heuristically. We can kind of guess the answer because we just discovered that f to the power 4 was 2 pi squared times identity. So it is kind of telling you that 2 pi to the minus half times f, fourth power is equal to the identity. This guy here, its fourth power is the identity, so I would expect, okay, with quotation marks, I would expect the eigenvalues to be the fourth roots of unity. We know it is a unitary operator, this operator on the left, 2 pi to the minus half f. And for unitary matrices, we know that the eigenvalues have unit modulus, they lie in the unit circle. So I kind of expect that this here too, if the space is a respectable one like L2, the eigenfunction, the eigenvalues would be the fourth roots of unity. This is what I expect, right? And what are those? They are 1 minus 1 plus I minus I. I expect this is going to happen. I need to find the eigenfunctions. Okay. But here I am going to cheat a little bit and say, look, we already know the answer. We know the answer by studying the quantum mechanical problem of the simple harmonic oscillator. In the simple harmonic oscillator, what happened was the Hamiltonian of x and p, I set the mass equal to 1, Planck's constant equal to 1, the frequency equal to 1, etc. This is equal to 1/2 x squared plus p squared in suitable units. Okay. Now as far as wave functions are concerned, if I take an abstract state psi and look at it in the position basis, this is what I call the position space wave function psi of x in the position basis. What is p represented by in the position basis? Minus I h cross gradient whatever, and h cross has been set equal to 1. So this thing is represented by the operator 1/2 x squared minus d2 over dx2 when it acts on functions of x which are in L2. And what is it represented by in momentum space? Well, in momentum space, the representative I am looking for is this guy, p psi, and this is what I call psi tilde of p, and these two fellows are Fourier transforms of each other. And the reason I know they are Fourier transforms of each other is because I know that this guy xp is essentially e to the power minus ipx over h cross or whatever it is, apart from square root of 2 pi h cross. This guy here is a kernel that will take you from one basis to another, either this or its complex conjugate. What's x represented by in the momentum space? Pardon me? Well, P is represented by minus IH cross D over dx, and this operator is represented by that when it acts in position space, but X operator is represented by plus IH cross D over D plus. Only then can you maintain the commutation relation X commutator P is IH cross times the unit operator. Well, for the square it does not matter whether it is plus I or minus I, so this becomes 1/2 P squared minus D2 over dP2. In other words, they become exactly the same. The operator is identical, and you want the eigenfunctions to be normalizable, and we know the complete set of eigenfunctions. They are Gaussians multiplied by Hermite polynomials, and they must be the same apart from constant multiple factors, multiplying factors, right? And those factors will be the eigenvalues, as you can see. So if I call the eigenfunctions here, remember that this operator, this H, has got eigenstates labeled by some non-negative integer n, 0, 1, 2, 3, etc. And this guy here, the position space thing, let us call that phi n of x. We can write this down. This normalized, I am going to normalize it, although that will not matter for this problem, 1 over square root of pi to the half 2 to the n factorial e to the minus x squared over 2, the Hermite polynomial Hn of x. Those are the normalized eigenstates, eigenfunctions in position space for the simple harmonic oscillator. And what's this guy here is the Hermite polynomial. It satisfies a certain differential equation, second order differential equation, and Hn of x has the property that when n is even, it is an even function, when n is odd, it is an odd function. Because this Hamiltonian is invariant under x goes to minus x, under parity. It commutes with the parity operator. Therefore, this Hamiltonian and the parity operator share eigenstates. In other words, since the levels are not degenerate, you can assert that each level, each wave function must either be an odd function of x or an even function of x, and similarly in P space. And these fellows here reflect that parity. H0 is 1, H1 is 2x, H2 is some x squared and constant, and so on and so forth. What is about this? Well, Pn equal to phi n tilde of P, this is equal to, apart from this factor, which we are not interested in at the moment because it is some independent normalization factor, it is e to the minus x squared P squared over 2 Hn of P times some factor. Okay. We discover what this factor is. It is a normalization factor of some kind, right? But this is the Fourier transform of that, and it looks exactly the same as that function, right? So this means these are the eigenfunctions of the Fourier transform operator. What we need to do is to find the eigenvalues and explicitly see if this is true or not. In other words, is the Fourier transform of this operator equal to this or not? That is what we got to check, right? And if that is true, we have found what the eigenvalue functions are, and of course once you check that out, the eigenvalues will also drop out. So let us do that, and the simplest way to do this, since I do not have a table of integrals where I can actually write down the Fourier transform of this guy, let us do the following. Let us use our famous generating function. So we need a generating function for the Hermite polynomials, e to the n over n factorial Hn of x is given by e to the power 2tx minus t squared. This is the generating function. Okay. So I do not remember the differential equations, I do not really remember all the normalization factors, but I remember all the generating functions, because from that you can always derive everything else. Okay. Okay. Now a relation like this, you should really, we are interested in real values of x of course, but a relation like this should always be looked at as soon as you have a power series, you should think of it as an analytic function of this variable in which the power series is expressed. Okay. What is the radius of convergence of this in T? What do you think it is? Well, look at the left hand side. What sort of function of T is it? It is an entire function. It is an entire function. It has got e to the t squared, e to the t and so on. So no finite singularities at all. So what is the radius of convergence of this series? So this so we can play with this series. Otherwise you got to worry. So I need the Fourier transform not of this guy but of this fellow. So let us multiply both sides by e to the power minus x squared over 2, and then when I take the Fourier transform I have dx e to the minus ikx, so minus and integrate from minus infinity to infinity. Okay. So I multiply this minus infinity to infinity dx e to the minus x squared over 2, so e to the minus ikx e to the minus x squared over 2 x. This has got to be equal to this. But what is this equal to? This is summation n equal to 0 to infinity t to the n over n factorial. This is the Fourier transform of what we want, of that wave function. So it is the Fourier transform of e to the minus x squared over 2 hn of x. And that is equal to this. This is a Gaussian integral, right. So let us write it out. This side here is equal to dx. This is equal to e to the minus t squared and then an integral minus infinity to infinity e to the minus x squared over 2 plus 2t minus ik times x. This integral converges, there is no problem because of this. Even though this is imaginary or complex, it does not matter, converges. This takes care of it. How do you do such an integral? Complete squares. We know the formula already, so that is again a useful formula to remember. The formula is an integral du e to the minus au squared plus bu minus infinity to infinity is square root of pi over a e to the b squared over 4a. And what condition do you need on a for this? This had better provide a damping factor, right? Yeah, real part of a greater than 0. What condition do you need on b? Do you need any condition on b at all? No. Arbitrary, including complex values, we do not care. So this thing here, this integral is equal to e to the minus t squared. So let us write this as exponentials, that is what makes it easy. By the way, in this case a is equal to a half. So you got square root of pi over a, that is square root of 2 pi. So let us keep that factor 2 pi, square root of 2 pi, and then you have exponential of minus t squared plus b squared over 4 times a. So b squared is 2t minus ik whole squared over 4 times a is a half, so there is a 2 here. Which is equal to square root of 2 pi exponential of what happens now. This is minus t squared, and then you get a 4t squared over 2, so that is a plus 2t squared, and then minus 4t ik divided by 2, so minus 2t ik, and then a k squared minus k squared over 2. Okay. So we end up with the fact that this thing here is equal to square root of 2 pi e to the minus k squared over 2, that factor, and then e to the power minus 2t ik, that is this factor, plus t squared, right. So let us erase everything else. This had better work out because I am not all that goes. All right, but now what happened? Well, remember I said that summation n equal to 0 to infinity e to the power 2tx minus t squared, sorry, this guy here was equal to a summation n equal to 0 to infinity t to the n over n factorial hn of x. I need to write this in that form. So let us write it as 2k times minus it. So this is equal to root 2 pi e to the minus k squared over 2 e to the power 2k times minus it plus t squared, which is minus it whole squared. Right? And that in turn is equal to square root of 2 pi e to the minus k squared over 2. And now let us use this formula once again. The fact that t is complex does not matter, we have already seen it is an entire function. So I replace t by minus it, and this becomes summation n equal to 0 to infinity minus I to the power n t to the power n over n factorial hn of k. Right? Okay, we are almost there. So this thing finally is equal to summation n equal to 0 to infinity square root of 2 pi into minus I to the power n times t to the power n over n factorial e to the minus k squared over 2 hn of k. Both are absolutely convergent power series in T. You can equate coefficients. So it tells you that the Fourier transform of this function is this function itself, the same function, multiplied by minus I to the power n times square root of 2 pi. Right? So it says now, therefore, putting in the normalization factors, you have 1 over square root of pi to the half 2 to the power n n factorial e to the minus x squared over 2 hn of x is an eigenfunction of the operator f with eigenvalue square root of 2 pi times minus I to the power n. So those are the eigenfunctions in L2. Just as the parity operator had eigenfunctions in the even and odd eigenfunctions of the harmonic oscillator were eigenfunctions of the parity operator also. And of course highly degenerate. You have an infinite number of eigenfunctions in L2 for each eigenvalue, every fourth one. So n equal to 0 has eigenvalue 1, 1 has eigenvalue minus I, 2 has eigenvalue minus 1, 3 has eigenvalue plus I, and the fourth one again has eigenvalue 4. This again has eigenvalue 1 and so on. So we used our knowledge of quantum mechanics. We used the fact that you have a Hamiltonian which look exactly the same in x and p, and in this case it was also a function of x squared and p squared, so you didn't even have a complex conjugation involved, but you had exactly the same differential operator, and we know its eigenvalues in L2 and eigenfunctions, and they immediately tell you, this directly proves that you have, these are the eigenvalues of the Fourier transform operator. So you have an integral operator, and we found its exact eigenfunctions and eigenvalues in this case. This doesn't, this happy circumstance doesn't always happen, but in this particular case it did.